All right. Hi, everyone. My name's Joe Barnard. Can everyone hear me? Seems like probably. Yeah, my name's Joe Barnard. I run a company called BPS.space. If you're not familiar with what we do, I think I'd like to start this out by just going ahead and giving a brief overview of what the company is about, or what the project is about, rather, and then how it became a business. And then we will get into what the title says, which is basically what has been going on in the last year. And I'm super excited to cover it because there's a lot of cool things in the works, and we have a lot to get to, so let's get started. So just a little bit of background on me. I grew up loving two different things. One was engineering and science, and the other was music. So there's me with a report in, I think, 4th grade on Robert Goddard with, liquid rocket engines and everything. And then on the right is some questionable fashion choices and haircuts from middle school playing guitar. And so, of course, like with this music and engineering thing, at some point you kind of have to make a call. When I decided to go to college, I chose the Berklee College of Music. And I ended up studying audio engineering there. So this is working with signal processing stuff, a lot of work in the recording studio, and just a lot of work with acoustic modes. But anyway, it's a music degree. So about halfway through Berklee, about halfway through school, I ended up picking up a video camera and got totally hooked with that. So I ended up starting to shoot music videos. Actually, the thing that turns out to be really good if you're in college and want to make money is to go somewhere where people need music videos, like a music school, and then shoot them, shoot the videos. So the other thing I did was wedding videos. You can see a photo of that on the right, and basically that was my job for a little while. So after I graduated, I worked in the wedding industry for a little while, which is not so much fun, but I did it. And then at some point I was bopping around online and I found this video that most of you have probably seen. It's the Falcon 9 Dev-R test from SpaceX in McGregor, Texas. And what they do is basically they fire the rockets on the ground, they bring this big vehicle up to like 1,000 meters or 500 meters. I mean, this thing is insanely big. But they bring it up there, they sort of test out their flight software, their flight dynamics, and what they're doing is this is before they had actually landed anything. And so the goal is just to test. So I see this video online, and there's this moment in my head where it's like, uh-oh, I picked the wrong career. Right? It's like, I have to be building this stuff. I really want to do this. And there are basically, I wanted to do this, and I had this issue in the way. And the issue looked a little bit like this. It's a music degree. And so, you want to be taken seriously if you want to try to get an interview with one of these aerospace companies. And a music degree doesn't get you super far. And so this is a very expensive piece of paper, and I wasn't really in a great position to buy another very expensive piece of paper. I didn't want to go back to school, so I figured, I have to teach myself and then demonstrate that I could teach myself if I wanted to be taken seriously to get a job in the aerospace industry. And my thought, it was a literal shower idea where I figured I could probably build an advanced model rocket that could take off and land just like the Falcon 9, just like SpaceX. And just so we're clear, like super naive at that time, I thought maybe it could take about 4 months total. And I'm here today, and it's been about 3.5 years. But anyway, so how do you go about this process of teaching yourself something, right? I really had no business getting into rocketry, and if you would ask my parents at the time, I think they would probably say the same thing, maybe in more strongly worded. But how do you go about doing this? So I went through a couple of methods here. The first is I bought a bunch of textbooks, and I just read through them all. And if you're getting started, I recommend these two books really highly. This is Rocket Propulsion Elements by George Sutton, and it's about exactly what it sounds like. And then Structures by J.E. Gordon. That's a structural or mechanical engineering book. It's a really great place to get started. And then I looked for some other tutorials. This is a tutorial series that I really love from Jeremy Blum that teaches you how to get started with the Arduino development platform. It teaches you a little bit of electrical engineering, coding, software design, stuff like that. But the thing that by far was the most valuable when I was learning is iterative design. And sort of what that looks like is you just get started. There's no good way to explain this, but you build whatever you can at the moment. And so this is like my first CAD model. It's a couple rectangles and some cylinders. And that thing is not going to space, for sure. But you start there, and maybe you print it out on a printer, or you do a little bit of analysis, and then you move to something a little bit better. So you add a little circle so it can sit nicely inside the rocket, and you revise it again, and basically each iteration, even if you're not really trying to, these things just improve. So the most important part for me was honestly just getting started so that I could iterate on the design after that, and not being afraid to just almost certainly fail the first few times. And so, speaking of failure, the first year of launches was totally successful, and nothing failed at all, and it was just really great. And that's a joke that no one seems to find funny, but I find it funny because there's no other way for me to deal with it. The first year of failures, first year of launches for BPS was a total failure. There were 10 launches in total, roughly one every 5 or 6 weeks. Each rocket was brand new, it was built. Dan was actually in attendance in a lot of these launches and can confirm many failures. But I'm going to go ahead, just because I'm a little tight for time, I have a lot to talk about today. So we're going to go ahead and look at the first 10 launches in rapid succession, and I'm going to try to explain, as they're happening, what exactly failed. They're all bad. Here we go. All right, so this is Scout V0.1. This first launch failed because of mechanical stress in the thrust vector control mount. The second launch failed as a software error. The third launch was a hardware error. The fourth launch was kind of lucky, but I promise it was just luck that made this work. Because the fifth launch failed with a TVC misalignment. The sixth launch, I couldn't even get this thing off the pad. It just wouldn't let. The seventh launch was a TVC error. The eighth launch was a simulation error. The rocket was too heavy. The ninth launch was an integer overflow in the flight software. And the 10th launch, I kid you not, I forgot to turn on thrust vector control in the flight software. And it's going to orbit there. So this is awful. 0 out of 10 rocket engineers recommend going through the first year of BPS.space. And each one of these builds here takes a lot of time, takes a lot of effort, and it really is it's rough to see it fall flat. But again, with this iterative design thing, basically if you can kind of clench your teeth and get through the failures, you end up getting to launch number 11, where things start to work. And so here's what happened there. This is about a year and a couple months into the project, launch number 11.
Auto sequence start. 7, 6, 5, 4, 3, 2.
So we got the up part right, and that's about it. Right, but this is the first success, right? And something that I think is important to note here, again with this iterative design, is getting this first success is really, really difficult. But as soon as you can get this, as soon as you can, even if the vehicle, the parachutes didn't work quite right, still a lot of difficulties in the flight software, but even in this state, just getting one flight with flight data and parameters that I can point to and be like, cool, this is truth, this is where we can work from, so that I continue to have mostly successful flights. What I noticed is that the rest of the Echo test campaign was a lot more successful. So most of the flights were actually really stable and returned a lot of good data, as opposed to Scout, which had a success rate of, I don't know, roughly 0%. Echo had something on the order of 75 to 80%. Still not perfect, but much better. So you get these accelerating returns once you get that one success. It's just something I learned there. And so as the rockets were getting a little bit more reliable, and as things were progressing a little bit, I did this thing. I did this thing that I think some of you in this room have probably done before, and I'll run through what it is. Here's how it works. You sit down at your desk, and you're on your computer, you're online, you're buying some rocket parts. And you put a couple things in your cart. You get some airframes and some motor tubes and some motors, and then you go to checkout and you look at the price tag and you go, ooh. And you think, that's kind of a lot of money. And then you think, and this is where the problem starts, you think, I wonder how much I've spent total, for all the rockets. And this is really where the problem is. So I did this for BPS, and I realized I can either shut this down because I cannot afford to keep spending this time and money on this stuff, or I can try to make the project sustain itself so that it's not a total loss for me, at least. The goal is just to not lose money, really. And so I figured what I could do is I could sell a thrust vector control kit. We've been getting a couple requests for it, and I figured, well, let's give it a shot. So in the same vein of iterative design, I taught myself how to design a printed circuit board. And again, it's just like, you find a couple of online tutorials, you get a friend to give you some tips and tricks, and then you mess it up a bunch until you stop messing it up. And so here's sort of how this looks. It's a little hard to see from down there, but basically this is a terrible, terrible PCB. It's like a rough design. It's the first one I did. But again, because it doesn't matter if you don't get it right on the first try. I get this board, I load some software on, I figure out what works, and then you get a better design with some cleaner electrical engineering, and then you move to a better aesthetic design, and then you clean up a little bit more electrical engineering, and at some point, you end up with a pretty respectable flight computer from something that certainly couldn't fly on the left. Just through iteration, you get to something good. And I did the same process for the thrust vector control mount. So this is the mechanics for the kit. You start with, I redesigned it all. You start with like a humble little cylinder here, and then you move up. You just sort of one thing at a time. You try to make sure that each time this thing gets printed on the printer, it looks a little bit nicer. And eventually you end up with something that honestly I feel pretty proud of in terms of the mechanics of the thrust vector control mount. And just for some specs here, so the mount can actuate plus or minus 5 degrees in any direction, both mixed or fixed between the two axes, so that's X and Y. And it can do that with an accuracy of about 1/4 degree. So because we gear down the servos in the TVC mount, I think a lot of you probably saw that at the booth today, but because we gear down these servos, you can actually get tremendous accuracy from what would traditionally be lower quality servos. It's just again, iterative design makes these things possible. So anyway, as part of the development process for this kit, I did a test campaign of a couple of different flights. This is just one of my favorites, so we'll walk through what it looks like here. Here are the chutes, and we get the legs. So we'll walk through it in slow motion here just to sort of explain what's going on. The motor lights via the pad. The rocket doesn't light the motor, but as the rocket lifts off, the flight computer detects that it has lifted off, and when you see that light turn red, it basically begins thrust vector control. And if you look close, you can see the movement, right? You can see the movement on the rocket as it's trying to gimbal the motor and keep itself upright. And so that sort of continues through burnout. It's logging a bunch of data, it's checking a bunch of sensors. And then after burnout, eventually we reach apogee, and you see this light turn off. That's the computer detecting that we have passed apogee. And then it switches to the landing configuration where it arms the parachutes to deploy, and then whatever altitude you set, basically it deploys all of the different pyro channels. So there's parachutes and legs on this flight. And so that's sort of the flight profile that I came up with just for the test flight, but of course most of these things are configurable. And so after a couple more test flights, I manufactured a bunch. These are all hand-assembled boards. And we did a really short and small production run of the Signal Alpha kit just to get lots of feedback from users. And this is the most important part, was getting feedback here. So with this kit, provided a bunch of instructions and a bunch of things to try to see, like, how much can I help people get started with this really complicated task? So I made a whole 40-minute video series on the right there of how do you go from having no rocket to flying that rocket with the Signal kit. And then, of course, lots of user manuals. Everyone loves reading the user manual. And then, so after selling these kits and getting a bunch of feedback from users about what worked, what they liked, and some things that could be improved, I moved on to Signal R2, which is sort of the current generation of BPS flight computers. So I'll just address the improvements here. Basically, we moved to a development version, and then finally the Signal R2 computer, which flies nearly all of the rockets that I build today. So a lot of the improvements are actually, you're not able to see them too well. It has to do with a lot of the improvements in flight software, error checking, things that basically are edge cases so that the computer tries to protect the user. But one of the biggest things that I ended up changing was I added a Bluetooth chip so you can talk to the computer with your phone. And it really is, this is like my favorite little pitch line, but it's like mission control for your phone. It's actually been really helpful, even on the experimental flights, to have this stuff on the launch pad. And of course, we did another test campaign with the R2 kit. So here's a flight of that. You can actually see the computer's lights on the right. And as it switches through different modes, the lights change color. Then we got parachutes.
Where's the parachute guy? Ah!
I put a little paratrooper in the parachute bay.
There he is! There he goes!
It's like my favorite.
Brave parachute man took a ride in the parachute bay of the rocket. Good job, little buddy.
Anyway, so we performed the test campaign in the same vein as Signal Alpha. I produced a whole new series. They're in like 4K too. They're really nice videos, but a whole new series of videos on how to build this kit. A lot more polished than Signal Alpha, just learning as I go. And then as part of this, I built a Rocket Lab Electron model that I published all the files for, and like you can build it if you have the kit. There's all decals and stuff. Anyway. And that sort of brings us, and then here's just some photos of production. And the Signal kit is still for sale today. It's still doing pretty well. And that's kind of where we're at. So that basically brings us to what else has happened since last year, around this time. I sort of count the year by when NARCON is, rather than New Year's. But in the last year, we've done a couple of things. And I guess we'll start here. So slow burning propellant has been something I focused on in last year's NARCON presentation, where I sort of addressed that in order to have really realistic model rockets, you want to have a very slow ascent from the launch pad. If any of you watched the DM-1 mission, or really any orbital launch, these rockets just crawl off the launch pad, especially when they're launching. And so to do that, you want slow burning propellant so you can stay in the air for a long time. And so let's look at the current options in the model rocketry community. So you have like the Estes E9, which, reliability aside, burns for about 3 seconds when it doesn't blow up. And then you have something like the Estes F15, so it's 3.5 seconds. You could go with the E6 or the F10. These are all great options, but they're not enough. The Saturn V takes 7 seconds to clear the tower. And so if you want to simulate that, you need a longer burn time. And so I gave this presentation where I said I wanted longer burning motors, and I'm not a propulsion engineer. And Gary from Aerotech came up after and said, tell me the specs and we'll build it. And I kind of thought he was kidding, and he's not kidding. Aerotech has made the G8, which burns for nearly 18 seconds. And there's no good way to describe it other than to watch it in real time. So here's a flight of one of the earlier G8s produced over the summer. It's all real time, and so here it is. You get that really slow liftoff. And it goes, and it goes, and it goes. And eventually there's some instability in this flight too. That's not the fault of the motor, but... And then it falls forever. There you go. So that's the G8. They didn't even just produce that too. They ended up making the G11 too, which is a slightly shorter burn, but we ended up flying the G11 with the Electron rocket that I built as part of the Signal R2 series. So here's that flight. And the cool thing about this is I was able to cram a camera inside the avionics bay pointed down toward the thrust vector control mount, so you can see it move in flight as it's trying to keep the rocket stable. Yeah, so it's working pretty hard. And then you got burnout, shoot, deploy, and clean touchdown. So the long burning propellant stuff has been really exciting to just be a part of in any way, and I can't wait to fly some more of those this year. But that's a big thing that happened last year. Moving on, I don't know, I got this tiny little rocket that I built. This thing is crazy. I can't emphasize how insanely difficult it is to make this thing fly. But let's talk a little bit about some of the details here. So in December of 2017, I sort of set out to make a Falcon Heavy model, being like, oh, well, I could probably make it work. And I really underestimated it, because I figured, I think at the latest we could launch in the spring of 2018, and it didn't happen until November. But essentially what we've got here is each core, each part of the rocket is thrust vector controlled, and it uses a internal use version of the signal flight computer. So on the bottom and top pictures here from left to right, we have the left core computer, the center core, the right core, and the upper stage. So each flight is complicated. The cores separate via a sort of a passive mechanical connection here, and so the way this works is so long as the side boosters are always pushing a little harder than the center core, they will stay attached. And as soon as the center core thrust, or at least the net thrust, exceeds the side cores, it will pull away like this. Now the side cores do have spots for separation motors, but I haven't used them yet. Those are more for like high stakes flights and things like that. Okay. The Falcon Heavy also has roll control, and I think this is maybe my favorite part of it. But basically, you can control roll. Like the space shuttle has a roll program. Most rockets have a roll program, and so like I had to put a roll program in the Falcon Heavy. So it launches, and then it rolls to about 20 degrees and locks in over there. And there's no point, of course. It just rolls because it can. But like, you know, you got to have a roll program. Anyway, this is a booster test flight. And speaking of test flights, so in the spring, I tested the center core. So this is just a flight test of that. It's a really gorgeous flame, too. This is an Apogee F10, I think. Pretty straight. Yeah, and then we got burnout. And come on. There it is. Got chutes, and then in a second you might see on the left the legs. There go the legs. And in the interest of time, we'll just move forward here. The next test flight was for the boosters. This is mostly focused on getting the side cores to work really well, ensuring that the roll program, those types of things worked. And the center core did have a guidance error. It was correcting way too hard, so it ended up slamming into and damaging one of the side boosters. But overall, still a successful test, because the primary focus was those side boosters. There it goes, it's correcting back to upright. And then in the second, we got center core ignition. And there it goes. So the center core really has trouble. I mean, to be honest, it's scale accurate. Like the real Falcon Heavy had trouble with the center core, so like maybe it's intentional. Anyway, you got chutes out. We're not going to wait for this thing to come back down to the ground. So the next test flight was the second stage. I had a lot of trouble getting this to work. You guys fly rockets, so you know why this is probably really hard to do. The center of pressure is way ahead of the center of mass. So the vehicle is naturally not just unstable, but like anti-stable. Right, so and it's a tiny vehicle, it's a very low mass moment of inertia, and it's somewhat of a high thrust for thrust vector control. But eventually I got the control loop to get fast enough, I got the response time dialed in, and finally a successful flight of the second stage on its own. Go. And now this flight did have a problem with it, and the problem happens when the fairing pops open. The fairing holds the parachute, and the parachute is supposed to come out, except that it doesn't, and the fairing just stays kind of closed. And the problem here is that it hits the ground.
That's usually the problem.
Oof. It's a pretty hard impact. Anyway, yeah, that's a problem. So as it turns out, I didn't run a thorough enough test campaign on the fairing to make sure that the parachutes would deploy for there. So I ended up running, or rather rerunning, a test campaign on how the fairing gets deployed. So all of this footage is shot at 1,000 frames per second and slowed down to like 1/5, or I don't know what the speed is, but it's 1,000 frames per second. And the way it works is essentially you've got 4 parts. You've got a base, 2 sides, and a nose cone. The 2 sides flip out because of the high pressure that the parachute pushes on it. And the parachute is in a Nomex blanket so that it's totally fireproof. And to be clear, I am not saying this is the most efficient or right way to deploy a fairing. I am, however, saying it's the method that uses the most black powder. So, you know,
Cool.
it's in that way it is the best. Anyway, so with all of that stuff tested, pretty much ready for the first launch. And I won't say anything, I'll just let the video play here. Yeah, so it's got a bit of a hold down. So a really clean roll program. Yeah, it looks like a real thing. You got stage set. Boosters do a little boot. And then you'll see there's some instability here. There's a real problem with the center core, and then the second stage fires the parachute. So what's going on here is there was a structural failure in the thrust vector control mount of the center core. And what ends up happening is the vehicle becomes unstable as it is flying upwards under its own thrust control. This is just some B-roll here. There's so much footage that I just can't not show this. Anyway, what ends up happening though is really cool because the second stage called an in-flight abort instead of firing its own motor. So I mentioned earlier that there's some more advanced error checking going on. With each flight, basically, I'm trying to think of all of the failure points and all of the scenarios in which the flight could go unsafe. And so when the second stage pops out that fairing, it's making the decision to not fire its own motor for safety because it knows that the rocket is pitched over too far. It's looking at a couple of different sources of data and determining this flight is not nominal, time to abort. So what ends up happening here is it was just sort of a build error in the center core, the reason that this structural failure happened. Should be a pretty easy fix for flight number 2, and that is coming up maybe like a month, maybe a month and a half, but I'm pretty excited for that. So, and there's one more shot. This one is kind of my favorite, actually. This is from the UAV that's circling the launch pad. And you can actually, if you look real close, you can kind of see the roll program. It rolls counterclockwise in this shot. You can just barely see it happen. Yeah, it's intense. But so moving on here, we're moving on. Something that I'd like to do in this year and a couple of the years going forward is get into more high-powered rocketry. And so part of that is sort of just learning more about it, learning more about the community and the people who launch HPR stuff. And something that I've noticed, something that is very clear is that safety is a lot more important in high-powered rocketry. And in a lot of the cases where either a dual deploy or a parachute deployment computer has failed, it seems to be mostly user error and not necessarily the computer's fault. It seems to be that the user didn't understand something about how the computer worked, or there was a build error or something like that. And so what I'd like to do is I've been working on a dual deployment computer called ARC, and the goal is, how can you make this thing foolproof, basically? In order to improve safety in the high-powered community, we've had actually a couple pretty serious issues with safety this year. And I just think the current options out there are not quite they're not quite intuitive enough. A lot of these computers require you to communicate with them via a series of beeps and buzzes and LEDs, or you have to bring a laptop out to the pad with 3 different dongles, and it's kind of it should be better than this. And so this is what ARC is. Basically, I'm focusing on doing something with 2 pyro channels for a main and a drogue. Each one of them has continuity detection, so it's should be able to understand on the pad if your pyros are actually going to fire. It's pretty important. A barometric altimeter up to 100,000 feet. Of course, you can go higher than that and use something like an acceleration-based altimeter, where you get velocity and then position from that. There's also multi-speed data logging. So I cannot get enough data. Like if there's gigabytes of data, of flight data after a flight, I'm really happy. Some people just want to know like how high and how fast, which is cool. I mean, that's kind of what high power is about. But okay, a couple other things. It has Bluetooth control. This is sort of solving the communication issue. Every single person, nearly every single person at the launch site will have a phone in their pocket. You should be able to use this computer to interface with your dual deploy computer so that it's more intuitive. You don't have to bring a bunch of stuff. You don't have to be like, oh man, who brought the cable today? There's too many stories of that not really working. And of course, trying to make this accessible to a lot of people under $100 total. So this is not built yet, but we do have a development board in the works. It's tiny. It's about a couple square millimeters smaller than the footprint of a 9-volt battery. So this, I'm not sure if this will be the final design for it. I'd like to make a couple other changes. And then in the spring, I think we're going to focus on some Mach Plus flights. What ends up happening is when you go through the transonic regime, the barometric altimeter goes like, what's going on? So I want to do a couple of those flights as a passive payload, and then we'll sort of move up from there. But there's no release date on this yet, just kind of trying to get it right. Anyway, so that is ARC. And then finally, propulsive landing. So when I started building the Signal Alpha kit in the spring of 2017, when I did that, like, think about how much you spend on rockets kind of exercise, I ended up putting propulsive landing on hold while I was building these kits. And eventually, the business became sustainable earlier this year, and we decided, or I decided rather, to focus back on propulsive landing again. So I'll go through just a couple of the tests that have happened so far. And I actually learned a lot this year in propulsive landing. So just a quick bullet point list of the things that I've learned. So first is, actually the only thing is that it's just super hard. It's like, it's a little bit like climbing a mountain in the fog, where you know you're getting closer to the top. Like I know I'm getting closer to landing, but I truly have no idea how close. You know you're getting close to the summit, but it's really hard to tell. So the vehicle that I've been working with is called Echo. Echo right now is performing a series of drop tests from a UAV where it's suspended about 30 meters above the ground, roughly speaking. Then it is dropped from the drone and it tries to propulsively land. And so this is just another shot of Echo here. Here are all of the components, and that's a photo from one of the flight tests. So basically, honestly, it is a pretty simple system. You've got one flight computer, a thrust vector control mount, some passive fins on the top, and here's what it looks like in flight. This is back in October. We get the legs out. Not quite. So we burned the motor a little bit too late there. The rocket was still moving a little too fast, and so because of that, that's why you see that late burn on the ground as the motor is still firing. And part of the challenge here is you want to fire the motor just at the right time so that when it burns out, you end up touching the ground. It's a very tricky balancing act. And so the opposite end of this is the test that I did in December, where we burned just a little too early. Out, and it's close though, it's close. And so the other thing that ends up having to happen with propulsive landing, at least with model rockets and solid non-throttleable motors, is you have to sort of accept either a bit of a hop when you touch down on the ground or a bit of a drop like that. The landing legs are spec'd to sustain at least a meter of a drop without braking, and so the real problem then that I've been focusing on for the last few weeks is horizontal drift. So what that is, I'll play another clip of this rocket, and what you'll notice is that when it's coming down, it's actually sliding to the side a little bit. So we can take a look at that now. Yeah, so see, it's just sliding. And that's, maybe if it wasn't sliding, it could have just sort of stuck it on the ground. And so there's a way that you can control horizontal drift. It's just a little bit complicated, though. I'll try to keep it simple for the presentation here. But if you want to, I'm happy to just geek out over this for a long time. And this isn't even totally correct. There are some errors in this, too. But basically, what you do is you track orientation of the rocket over time. So the rocket is not going to always be perfectly straight up. And the reason we get this horizontal drift isn't because of wind or anything. It's because at some point the rocket might spend 1 or 2 seconds pitched over like this, and it accumulates some speed in this direction. And so what you have to do is you have to track that speed regardless of the roll of the vehicle, and then you have to correct for it regardless of the roll of the vehicle. So you have to set global set points and then rotate them into the body frame. This is already getting way too deep into control stuff. If someone doesn't stop me, I'll just keep talking about it forever. But basically, that's the thing that I'm working on right now with propulsive landing is the horizontal control component. I think it's pretty close. I don't want to regret this, but I feel like we might stick it in 2019. It feels pretty close to me now. So we'll see. Maybe I'll look back at this in a year and be like, no. But anyway, yeah, so that's the propulsive landing stuff. There's just a couple more shots of Echo here. One is mid-leg deployment last fall, and the other is just before touchdown. So the other thing that I've been working on too, speaking of landing, is this video series called Landing Model Rockets. It's the YouTube channel for the business has actually taken off, pun intended, this year. And so something that I figured is I used a lot of online tutorials and information that people just put out because of the goodness of their heart when I started BPS. And I figure I've learned a lot through the program. And for the things that I know, I should be sharing that back with others. And so that's what Landing Model Rockets is about. Basically, if you had no experience and you were getting started, how would you go about building something like this? And of course, I haven't actually landed yet. So you're welcome to just ignore all of the advice in the series, but I do feel like I'm pretty close. So we'll see. Anyway, that's something I've been working on, and the series is all supported through a Patreon page where people pledge a monthly amount to get access to files or a chat room where we can all sort of bounce ideas off of each other for how you get this hard thing done. But this is actually one of the things that has really supported BPS as a project and has supported me spending lots of time doing it. With that, 2019, what is coming up next? So the next Falcon Heavy flight is the thing I'm focused on right now, along with the next landing test. I'm pretty sure the Falcon Heavy flight can happen in April, and the next landing test should be within 2 weeks or so. Feeling pretty confident about that. Of course, I'd like to focus on ARC pretty seriously. I think we're going to start moving into some higher power stuff. And with the talk about the higher power stuff, here's the little Steve Jobs thing, the one more thing. So a couple people have asked about thrust vector control in high-powered rockets. Certainly a cool idea, but I think actually what makes more sense in high power is to focus on augmenting the passive stability on the vehicle instead of trying to make something unstable fly. So instead of using thrust vector control, your rocket would still have fins, but you would just add to that stability so it doesn't weathercock or it doesn't do, it just has better stability during flight. And I think that is going to take the form, at least in my case, of a reaction control system or a cold gas thruster system. And so this is a really early test right here, just super early in the development process and low power vehicles. But this is a reaction control system where the rocket is sitting on a launch mount, or it's sitting on a rotating mount, and it tries to reorient itself back to upright. So it's naturally unstable, and it uses these gas thrusters to push itself back upright. So we'll take a look at that now. So the thrusters are at the top right there, and it's basically firing them to try to keep itself upright. Anyway, so that's something I'm also pretty excited for in 2019. I think that's going to be really fun and really risky to fly in high-power rockets, but that's like half the fun. So anyway, that's what I got for you today. Thank you all for joining. I'd love to do some questions if you guys have any. And yeah, thanks a bunch. Yeah, go for it.
Yes. Looking at photography is a big plus in rocketry. One of the concerns has always been to dampen or eliminate roll rates.
Yeah.
And is this something that your sensors will be able to do in terms of eliminating roll?
I thought about this earlier, especially for some high power builds. If you're flying like a 3-finned rocket and you get one of the fins just a little wrong, you're kind of going to spin a lot. So the sensors can certainly keep up with tracking the roll. The TVC system on its own cannot control the roll. The reaction control system, however, could definitely do that. There's also, I mean, there's like 1,000 things that I want to do, but one of them, I think, to control roll, and even if you put it in a passive rocket, one of the ways you could do this is you could have a spinning gyroscope, like a fairly decent sized mass, as long as you're willing to take a little bit of a mass hit in the rocket, and that would basically, as a control moment gyro, change or augment the roll on the vehicle. I think that might be a good way to do it too. But I think the answer to the question is the sensors can certainly look at roll. All the rockets that I have and all the computers, they log the roll of the vehicle. Yeah. Sure.
Running to gimbal lock.
Yeah. Great question. Thank you for that question because it allows me to brag a little bit. So the question is, do you run into gimbal lock? And gimbal lock is this phenomenon that happens with what's called basically axis angle representation of orientation, which is basically what's your rotation in X, Y, and Z. And the problem with this is actually something that the Apollo astronauts had to deal with when they were flying their spacecraft, is there are a couple of points that you cannot orient your spacecraft near, because if you do, you'll lose the resolution of one of the axes, and that's called gimbal lock. And so I don't run into gimbal lock because all of my flight computers have switched from direction cosines to quaternions. So yeah, it's the math makes you kind of hate everything, but it's too bad too, because they're like the most complex and hard to understand representation of numbers and orientations, but they are the most computationally efficient, and they're also the safest for vehicles like a Falcon 9 or anything that's doing flips around in the air. I would put lots and lots of money on the Falcon 9 using quaternions as well for their orientation stuff. Yeah. Yeah. Any other questions? Sure.
How many Patreon supporters do you have?
How many Patreon supporters do I have? I think I have 170 something. It's quite a few. Honestly, I can't, the generosity of some people has been kind of astounding, and I feel like I just owe a lot to those folks. The project certainly still wouldn't be around without that. So it's been kind of phenomenal. Yeah.
On the Falcon Heavy launch, there was a lot of sparks.
Yeah.
Early on. Is that purely motor-based, or did you have something else going on?
No, I would love to put smoke charges and fireworks and stuff in the launch trench, because that seems like a really good idea. But yeah, no, it's all motor-based. So these are black powder motors that are in the Falcon Heavy, and basically there are sort of two facets to this. The black powder motors sort of spew stuff everywhere. And I also launch usually at dusk. You'll see a lot of the footage is pretty grainy because of that. But if you're willing to accept some grain, the fire looks like 10 times as big. And you want to see the fire. Yeah, so the sparks, the other thing too is the sparks aren't great for the launch computer, but one step at a time, basically.
What motors were those?
I think so for the motors that I use, it's usually like an E9, an F15. Actually, the motors that I mentioned in the long burning stuff, basically all of those I've used. So it'd be the E9 or the F15, depending on the flight profile. And then for the composite stuff, I would actually like to get a composite motor in the center core. But it would be one of those Estes ones. Yeah. Anyone else? Yeah, sure.
Do you think some of your success has been
using your marketing skills that you probably learned in college and wedding photography to kind of leverage this current SpaceX hype?
Oh yeah. I mean, there's no, like, it would be wrong to ignore that, like, there's some non-trivial probably portion of the success of BPS that is due to a couple of things. One is I kind of look like Elon Musk. There's like nothing I could do about it. Like I did, yeah, you know, you got like the hairline and everything. But the other is, of course, if you put something you'll notice if any of you follow Tim Dodd, the Everyday Astronaut, what you'll notice is his videos that cover SpaceX get tons of views, and the videos that cover like the Parker Solar Probe, these tremendous engineering challenges, get very few. It's honestly just, you know, it's something that's kind of hard to fight. There's a lot of hype around SpaceX, and there's a lot of hate around other aerospace companies who are still doing really cool work. But yeah, I think there's probably some non-trivial amount of that I can credit to that.
And then my second question is, especially with you maybe branching out to high power, which maybe doesn't really lend itself to your gimbling the whole motor.
Yeah.
Have you thought about using jet vanes?
Jet vanes are so cool. Yeah. The thing with jet vanes is you have to have a motor that's big enough. So like Copenhagen suborbitals, if any of you guys follow them, they use jet vanes in their rocket to vector their thrust. But you have to have, okay, jet vanes are hard with solid fuel too, because the vanes get caked in solid propellant. And so the shape of them changes. It's a little harder to predict how they're going to change shape during flight. I think jet vanes are pretty cool. It's probably not something that I'll do for at least a little while. Yeah. Sure. Oh, jet vanes are when you stick small, usually they're graphite or some really high melting temperature object into the exhaust plume of the rocket. And so then you can sort of move those vanes that are in the exhaust plume, and it ends up being very similar to gimbaling the motor, where you're pointing the thrust in different directions. Right, well, it still ends up with vectored thrust. Yeah.
Instead of having the vanes actually into the exhaust, have you ever thought of just coming straight?
Like a fighter jet. Yeah, like a fighter jet does. That would be a cool way to do it, and certainly an easier way at this scale. Yeah, I think I would have to do some math on like the thrust losses that you get there.
Cut down on the caking.
Yeah, that might be a way to do it. Yeah. Yeah, there you go. Just use the Air Force.
Using the thrust vanes to throttle your engines for landing control.
Yeah, it's just, so for the landing stuff, I'm like right up against the mass budget right now. And so it's very difficult to justify adding more hardware if I can just try really hard to get all of the other control stuff in line so that I can land it without throttling. I think if I need to throttle, the way to do it, I have this, I won't go all the way into detail, but basically you have a couple of outboard motors that either thrust up or down to augment the existing thrust of the motor and just sort of add to the total impulse. Yeah.
One other quick thing. You mentioned F-15s as a choice.
Yeah.
Are you tormented by the fact that you would like to have more specific impulse for what you need?
Yes.
In terms of the weight of what you have to deal with a relatively light impulse motor?
Yeah, I think it's an unrealistic thing for me to ask for this, just because I don't really know where the limits on black powder motors are. But I would love something that is twice the thrust of an F-15, even if it has to be classified as level 1 or HPR. Just because of it looks gorgeous. Like, I just can't get over as someone who likes photography, like I can't get over the look of those black powder engines. Yeah.
What about using a hybrid? I know a lot of times hybrids get lower thrust.
The hybrid thing is really tricky. They end up being a lot more complicated than it seems like on the surface, because you end up dealing with a lot of plumbing. Depending on your setup, you might end up dealing with N2O, which is like not super safe. And my buddy Charlie is this brilliant engineer. He has this saying that it's basically like hybrids are all of the drawbacks of liquids and none of the benefits. So if you're going to go with a hybrid, just like build a liquid. Yeah. Yeah. Anyone else? All right, well, I think that's it. Thank you guys for coming.